So in the next section, we're going to talk about the multiplication rule for probability. We talked about mutually exclusive events in the last section, and mutually exclusive means that the two events cannot happen at the same time. You can't be both male and female at the same time, or a freshman and a sophomore at the same time. You can't draw a card that is both a heart and a spade at the same time. Those events are mutually exclusive. Okay, mutual exclusivity is different than talking about events being independent. Independent events are events that if you know that one has happened, it doesn't affect the probability of the other one happening. So for example, if we flip a coin, we know that we're either going to get heads or tails out of that. Then if I come back and I pick up the coin again and I flip the coin again, then I could still get either heads or tails. Okay? Knowing that I got heads on the first flip does not affect or change the probability of the next time when I pick up that coin. I still have a 50-50 chance of getting a head or a tail there. Okay? So flipping a coin and then flipping it again and repeating that event. Same thing with drawing a card over and over again, as long as I put it back each time. Those events are independent. Drawing a card out has a 1 out of 52 chance, an individual card, and knowing that I draw the ace of spades the first time doesn't change the probability of me drawing it the next time. Now, two events are dependent if the outcome of the first affects the probability of the second. So maybe I draw a card and I keep it. Okay, so I draw it, I look at it, and I set it aside. And then I go back and draw again. Okay, well, the probability of me drawing whatever it is that I'm looking for in that second card has changed since I kept the card out the first time. I now have a probability out of 51 instead of out of the 52 cards that were there. Okay, these two events would be dependent. Okay, knowing that one has happened affects the probability of the other one. Okay. If two events are independent, so back to independent events here. If two events are independent, if I want to know the probability that both A and B happen, it's the product of the two probabilities. So if I can find a way to slide this stuff down, okay, to another thought. If I want to flip my coin and I want to know the probability of flipping a head, we know from before that there's a 1 in 2 chance of flipping a head. And maybe I want to flip another head. So head and then head. If I flip that coin 2 times, and I want to know the probability, that means and, that I flip a head and a head, it would be 1/2 times 1/2, which is 1/4. Also, if you go back to the tree diagram that we drew back in the last section, I forget which video it's in, and we had those two flips where we had a head, 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 tail, tail, head, tail, tail in our tree diagram. We had already determined that the probability of getting 2 heads in a row would be a 1 in 4 chance. Maybe I'm going to draw a card and I'm going to put it back when I'm done. So I'm going to slide these guys all the way down, completely out of my, out of my line of sight. Draw a card. I'm going to put it back. And then I'm going to draw again. This is supposed to be a D here, all hooked together. And what I want to know the probability that I'm going to get a heart, and then a 9. The probability that I get a heart, and the probability that I get a 9 for my 2, I'll say, and then a 9. Since I am putting the card back and shuffling the deck again before I draw the second time, the probability that I get a heart is 13 out of 52, okay, or 1 out of 4. I can reduce it before I find my product if I want to. The probability that I'll find or draw a 9 next, there's 4 of those out of 52. So I have a 1 in 4 chance, I have a 1 in 13 chance. Altogether, that's a 1 in 52 chance that I would first draw a heart, and then when I put it back, I would draw a 9. If my events are independent, then the probability that both of these two things happen is the product of their probabilities. If we have a dependent situation, however, then we're going to have to talk about conditional probability. Okay, conditional probability is written with a straight line, a straight bar in between my two events. The way we would read this is the probability that B would happen given A has already occurred. So whatever's here in the second place, that's the event that I told has already happened. So for example, if I want to find, back to my deck of cards, I'm going to draw a single card again. If I want to find the probability that I draw a heart, we did that on the other page, 13 out of 52, which is 1 over 4. If I want to find the probability that I draw 4, I think I had 9 on the other page, so we'll say that. There's 4 9s out of 52. 1 out of 13 chance. Maybe I want to find the probability that I've drawn a heart, given that the card I drew was a 9. Now your author will have in there, it's on down the road a little bit in the book, but it'll have a formula for finding conditional probability if you need it. Okay, but some of these we can do without a fancy formula. If I'm told that for sure already that the card that I'm holding, you said pick a card, any card, and I said, I'm holding a 9. And if you know that I'm holding a 9 in my hand, you've narrowed it down to how many cards? There's 4 in the deck. Now, of those 4 9s in the deck, how many of them are hearts? If there are 4 9s in the deck of cards, how many of those cards are hearts? That's equal to 1. If I want to find the probability that I have drawn a red card, given that it's a jack, the jack is the piece that's given to me. So I think, well, how many jacks are there in the deck? There's 4. Of those jacks, I missed with my arrow, how many of them are red? 2 of them are red, and 2 of them are black. So the probability that the card, if I told you a part of it, I'd pick a card, any card, and I draw one in my hand. And you say, well, at least tell me what you're holding, and I say, hey, it's a jack. The chance that the card I'm holding has a 50% chance, or 1 in 2 chance of being red, and a 1 in 2 chance of being black. What if I want to ask something like, what's the probability that it's a jack, given that it's a spade? Can't draw a spade, so I'm going to write the word spade. If I'm told that my card is a spade already, that narrows it down to 13 cards. Of those 13 spades, How many of them are jacks? Only one. We can use conditional probability to tell us whether or not two events are independent. Two events are independent if the probability of B given A is equal to the regular probability of B. Meaning, me telling you that A happened doesn't change the probability of B happening. Okay, so we can check for independence this way. Up here, we said the probability that I draw a heart, given that the card was a 9, is 1/4. The probability of drawing a heart out of a deck without giving any extra hints, anything else being told, is 1 in 4. It's 1/4. Okay, since these two are equal, that means the events drawing a heart and drawing a 9, that says draw, are independent events. All right, drawing a jack, given that the card was a spade. If I wanted the probability of drawing a jack out of the deck without knowing anything else, there are 4 jacks out of 52 cards, which still reduces to be 1/13. Okay, these two events, the event drawing a jack, drawing a spade, also independent events. I'll show you some examples that aren't independent in the next video. This one got too long, terribly.